Have you seen this giant machine? This is called a locomotive. A locomotive is a self-propelled vehicle that runs on rails and is used to carry railroad cars. Locomotives can be powered by various means, including steam, diesel fuel, and electricity. This is an electric locomotive, but how this locomotive works? Today, we will delve into the fascinating world of electric locomotives, specifically how they work. In recent years, hydrogen-powered locomotives have also been introduced in some countries. Based on the current, electric locomotives can be broadly classified into two types, AC and DC, although both are powered by overhead lines, but the difference is which type of motor they use, AC or DC. In a typical electric locomotive layout, there are four key areas: the driver's cab, the rooftop, the underframe, and the machine room. The driver's cab is a compact area where the driver operates the locomotive. On the locomotive's roof, several critical components are located, with the pantograph playing a vital role. Under the locomotive, numerous electrical components are housed, including the transformer, which is a crucial part. Inside the locomotive contains a variety of components. Now let's explore how this locomotive functions. First, we need to get that pantograph up, but it is controlled by a pneumatic system. Think of it like using air pressure to make it move. So here's the key question: where does that air pressure come from? A small air compressor within the locomotive, powered by the battery, is used to build up air pressure. Once the air pressure reaches 5.5 kilograms per square centimeter, the pantograph can be raised. Next, the single-phase AC power is delivered to the transformer, which is located beneath the locomotive. Here, the transformer steps down the 25 kilovolts AC to the required voltage. The lower voltage AC is then converted to DC by a rectifier. Inside the electric locomotive, the electrical components are housed in modular enclosures or cabinets. Crucially, for AC traction motors, the DC is then converted back to AC by an inverter. However, this is not the original 25 kV AC. The inverter creates a variable frequency AC. This variable frequency is what allows for the precise control of the AC traction motor speed and torque. In some older electric locomotives that utilize DC traction motors, where a tap changer is employed to control the train speed. Essentially, the tap changer, which is part of the locomotive's transformer, works by switching between different taps on the transformer's secondary winding. Think of it like a multi-position switch that selects varying voltage outputs. By doing this, we effectively change the voltage supplied to the DC traction motors, and that voltage variation directly controls the motor's speed. Finally, the AC is then fed to the AC traction motors. The rotating traction motors then turn the locomotive's wheels through a system of gears. Observe how this gear mechanism interacts with the motor rotor. This is actual footage of the motor and wheel assembly. Finally, the train moves. During motor operation, heat is generated. To mitigate this, forced air is directed into the motor to cool its internal components. Due to the various electrical components housed within the machine room, a blower is also used to cool the locomotive's machine room. In this view, you can observe the blowers throughout the locomotive. This is an air vent. Through this opening, air is drawn into the blower. During operation, various protective components are installed on the locomotive's roof. This is a surge arrestor, and this is a VCB, or vacuum circuit breaker. The VCB is a crucial component. It acts as a high-voltage switch controlling the flow of current from the pantograph to the transformer. While we observe a variety of electric locomotive designs worldwide, it's true that the fundamental operational principles remain largely consistent. What are your thoughts on this? Share your comments below. Thank you.